Hello, in this video we will solve the logistic differential equation. The logistic differential equation is a differential equation that describes population growth. P here is some population, dp dt is the rate of change of that population with respect to time. The logistic differential equation models the rate of change of population with respect to time as some constant times the current population times 1 minus p over m. M here is called the carrying capacity. We won't discuss the origins of this differential equation or why it can be used to accurately describe some population models. In this video, we wish to solve this differential equation to find the function p, the population, with respect to time. This is a separable differential equation. We're going to divide both sides by this expression and multiply both sides by dt. If we do that, we have 1 divided by p times 1 minus p over m times dp equal to k times dt. On the left, we're going to multiply the numerator and denominator by m. We distribute the m into this factor in the parentheses, and we have m divided by p times m. M times p over m is p. Now we want to integrate both sides. The variable on the left is p, so we have a rational function. We are going to solve this using separation of variables. We'll do that off to the side. Remember that p is the variable here. We treat p like we would ordinarily treat x. So we want to write this rational function as a fraction with a denominator of p plus a fraction with a denominator of m minus p. Multiply both sides by the full denominator on the left, and we have m equals, the p's cancel for the a term, so we have a times m minus p plus b times p. Simplifying, we have a times m. Remember that the variable that we're interested in is p. So we have am minus ap plus bp, so that's b minus a times p. This is all equal to m. Once again, the variable that we're interested in is p. So m is a constant term, am is a constant term. M equals am. That means that a must equal 1. There is no term with a factor of p on the left, so b minus a times p must equal 0. That means that b equals a, which is 1. So using partial fraction decomposition, we can write this first integral as 1 divided by p plus 1 divided by m minus p dp. The antiderivative of 1 over p is natural log the absolute value of p. The antiderivative of 1 over m minus p is negative natural log of the absolute value of m minus p. On the right-hand side, the antiderivative of k is simply k times t plus some arbitrary constant. Let's multiply both sides by -1. It will make some simplifications easier later on. If we multiply c times -1, well, c is an arbitrary constant, so we can leave it as plus c. When we have the difference of two logarithms, we can write the argument of the positive one divided by the argument of the negative one, m minus p divided by p. We want to solve this expression for p. That's our variable that we're interested in here. That's the population function. We raise e to the power of both sides, and we have the absolute value of m minus p divided by p equal to e to the negative k times t times e to the c. E to the c is a positive constant. So we could express this as e to the negative kt times a, where we understand that a is some positive constant. To deal with the absolute value bars, this positive constant could be either positive or negative. So to deal with the absolute value bars, we have m minus p divided by p equals, and instead of having some positive constant times e to the negative kt, we can express this as any positive or negative constant times e to the kt. We want to solve this expression for the function p. We multiply both sides by p, We add p to both sides. And then on the right, we can factor out a p. P times c times e to the negative kt plus 1. Finally, to solve for p, the population, we divide both sides by this expression. P equals m divided by c times e to the negative kt plus 1. It turns out that we can determine a meaningful value for this arbitrary constant c. If we go up to this expression here, if we imagine what the value of the population is when t equals 0, we could call that population p sub 0 for the initial population. So if t equals 0, this expression turns into m minus p sub 0 divided by p sub 0 is equal to c times e to the negative k times 0, or negative 0. E to the 0 is 1, so this is equal to c. In other words, for this logistic growth model, this constant c is the carrying capacity minus the initial population divided by the initial population. So we can write the final function for the population as the population in terms of t is equal to the carrying capacity m divided by m minus p sub 0 divided by p sub 0, that's the constant c, times e to the negative kt plus 1. This is the solution to the logistic differential equation.